All right, we're going to discuss the integral in terms of the method used to find it. Okay, and then later in the book, we'll give a more up-to-date treatment of the integral. Okay, first of all, if you have a function, f of x, a function capital F of x is called an antiderivative if the derivative of capital F is equal to little f. Okay. Now, the way we find an integral using an antiderivative is as follows. If we have a function, a up to b f of x dx, that integral is going to be the antiderivative at b minus the antiderivative at a. Okay? And we have in mind that f is a continuous function defined on the closed interval. Okay? Now, the first thing we need to do is we need to show that this definition is well defined. So I need to consider the case of another antiderivative and see if I get the same thing. So that's what this proposition is saying. It's saying that in fact it is well defined. If I have two antiderivatives, I'll get the same answer here. All right, so suppose I look at two of them, capital G and capital F, both of them antiderivatives of f, and I look at their difference. Call that capital H of x. Well, then h prime of x is equal to 0, because when I take a derivative, it's the derivative of this one minus the derivative of that one, which is just f of x minus f of x. So by the mean value theorem, if I look at h of b minus h of a, that's f at some, that's h prime at some point in between times b minus a, but you see h prime is always 0. So h of b minus h of a is 0. So that says that h of b is equal to h of a. Well, that says that this is equal to that. See? And now what I can do is I can subtract g of a from both sides and add f of b to both sides. And then I find the thing that I wanted to show. Now, the first thing you might wonder is, why would anyone want to do this? Well, here's a little example. Suppose a of x is the area under the graph of a non-negative function, f of x, which is continuous. So I have the graph of the function here, and a of x is the area between a and x underneath the graph of this function. So if I looked at a of x plus h, that would be all of this, see? And so if I look at a of x plus h minus a of x, that's this material in here, see? Now, if you have a situation like this where the function is increasing, then this material here, this number here, which I've got labeled here, is somewhere between f of x h and f of x plus h times h. Because you see, if I look at this, see, that would just be the area of a large rectangle that would have height f of x plus h. And this would be the area of a rectangle that's too small, that would have height f of x. So you see what happens here is, if I divide through by h, I see that this expression here is somewhere between f of x and f of x plus h. So now if I take a limit as h goes to 0, you get capital A prime of x equal to f of x. And of course, a of a, that would be 0 because it's just the area under the curve from A up to A. See? So if we wanted to define what we mean by the area under a curve, this is how we would do it. We would look for a solution to this initial value problem. And that's what this kind of thing is called. Okay, and so if I wanted the total area from A up to B, it would be A of B minus A of little a, and that would be the area under the curve, you see. So this is why we'd want to do this. This integral allows us to find the area under a curve, just as the derivative allowed us to find the slope of a tangent line to a curve. Here's an example. Find the area above the x-axis between y equals sine of x and the x-axis for x element of 0 to pi. Now what happens, what this looks like is I'm not going to show the graph, but you can show it if you like. It comes up like this and comes down like that, see. It is kind of a upside down U-shaped thing. And so the integral from 0 to pi of the sine of x dx is this area, because this function is non-negative on this interval. And now I observe that I know an antiderivative for this function, namely minus the cosine of x. So this integral is minus the cosine of pi minus the cosine of 0, and that's 2. So that's the area. Now there are two fundamental questions here that you've got to consider. For a continuous function f, why does there exist an antiderivative? This is a significant mathematical question, and we can give a good answer to this question. Second question is in a way harder. How do you find the antiderivative? Well, we'll know how to find a lot of antiderivatives by just going backwards in those tables of derivatives that I've presented in the chapter. And we can certainly find antiderivatives for polynomials. But in general, this is rather hard to do, and there will be a whole chapter on techniques for how to find it. And sometimes, no matter what we try, we just can't. At least not in terms of functions that we have names for. But just because you can't find a name for it doesn't mean it's not there. And that is what is considered in the first question. Okay, there's one class of functions that is particularly easy to take antiderivatives of, and that is polynomials. So if you have a polynomial, then you can say, well, let capital P of x be this. And it follows then that the derivative of capital P is little p. You remember how you do it. You bring down this exponent here and take x to the 1 less. And then that gives you this. For example, if you have P of x equal to 1 plus x cubed, then we could take, for an antiderivative, capital P of x equal to this. And so the integral from 0 to 3 of this, and incidentally this function is going to be positive on this interval, that is equal to this, 111 over 4, which maybe you would not have thought of. Okay, now remember some notation. We discussed the Weierstrass Approximation Theorem in the chapter on continuous functions. The norm of a continuous function is the supremum of the absolute value of f of x such that x is an element of a, b. Now for continuous functions, I could put maximum here by the extreme value theorem. Okay, also remember that if you have a continuous function defined on a closed interval, then there exists a sequence of polynomials for which the norm of f minus p sub n converges to 0. That's the approximation theorem of Weierstrass. So here is the major existence theorem that answers this first question. Okay? Let f be a continuous real-valued function. Then there exists capital F such that its derivative is little f on the open interval. And in fact, it has a right or left derivative at the endpoints of the closed interval. And so, for example, at a, the derivative of capital F would be little f of a. And that would be a right derivative. So the thing that is important to notice is that capital F will be continuous on the closed interval. So I'm going to let p sub n be a sequence of polynomials that converges to f in this manner as we just described. So that means p sub n of x is uniformly close to f of x on the entire closed interval. And I will let capital P sub n be an antiderivative for p sub n, little p sub n, lowercase p sub n. Now, by the mean value theorem, if I look at this minus this, and notice that there's two different indices, m and n here. Okay? I can rearrange the order here and write it this way. See? And now that is p sub n of t minus p sub m of t times x minus a for the inside here. See? And this is just by the mean value theorem. Now this expression is smaller than or equal to the norm of p sub n minus p sub m times the magnitude of b minus a. And now I can use the triangle inequality to say that this is smaller than or equal to the sum of these two times b minus a. Now by what we chose these to be, this converges to 0 as n and m get large. Now what does that mean? Well, that means that if I look at this function of x here, the sequence of functions here, that is a Cauchy sequence for each value of x. So that tells me that I can take the limit of this, and that limit will exist. The thing it converges to I will denote as capital F of x. And you see this is carried out for an arbitrary x in the closed interval. So now I've defined a function on the closed interval, and what I need to do now is show that in fact it is an antiderivative for the function little f. So I need to show this. So first of all, I'll look at right derivatives. So I will let x be in the half open interval here, and I'll just be looking at h bigger than 0 for now. Then by the mean value theorem, this is equal to this. Now notice what I did here. I subtracted off a p sub n of a from this term, and I subtracted off a p sub n of a from this term. Now why did I do that? Well, because this one converges to f of x. So what happens is this thing converges to f of x. This thing converges to f of x plus h. All right, this is going to be true for some t sub hn element of this open interval. By compactness, there's a subsequence, and I'm going to denote it as t sub hn, where n is going to infinity, and the limit of this is going to be some number t sub h in the closed interval. I don't know if it will be in the open interval, but it will be in the closed interval. So now I have p sub n of thn minus f of th. I want to look at this, and I want to show that as n goes to infinity, this expression converges to 0. Well, this is smaller than this by the triangle inequality. And now this is smaller than the norm of Pn minus f. And then I have this term here. By continuity of the function little f, as n goes to infinity, this thing converges to 0. Now remember, this is just a subsequence of these, okay? And I'm just denoting it with the same notation. This doesn't matter. Okay, so now I have this thing will converge to 0. So if I go up here to this expression that I have here, where is it? Right here. I can let n go to infinity, and this thing will converge to f of t sub h. This thing on the top will converge to capital F of x plus h minus capital F of x, see, according to this rule. So that tells me I have an expression like this. Where's t sub h? Well, t sub h is somewhere between x and x plus h. So as I let h converge to 0, by continuity of the function little f, this must converge to f of x. And therefore the limit of the difference quotient exists and equals the derivative by definition, and that equals little f of x. Now if you look at x in the open interval, you could also ask for a derivative from the left. See, this is giving me a right derivative, a derivative from the right. Okay, the situation's exactly the same, except you let h go to 0 through negative values. So now I'll just massage this expression. I get this is equal to this. And now I'll replace minus h with k and absorb this minus sign in the top, and I get something like this. And so when I look at derivatives from the left, it's really the limit as k goes to 0 from the right of f of x minus k over k. And now you do exactly the same argument that was done above and find that the left derivative exists at each point of the open interval, and also the left derivative exists at the point B, and it always equals f of x wherever x is. And so that shows the existence of an antiderivative for an arbitrary continuous function defined on a closed interval. Now, as an application, and as I mentioned, this is really an initial value problem. And this shows you how you can solve initial value problems of this form. If you want to get something with initial condition and y prime of x equal to f of x, and you're trying to find y, you just let y of x equal to capital F of x, which I know exists from what I just showed above, minus f of a plus y naught. Now suppose you want to find the area between two curves, f of x and g of x, for x element of an interval. This is an example. So you see f of x sometimes is on the top and sometimes it's on the bottom. All right, and I have a little chunk of area here. This little chunk of area is approximately equal to absolute value of f of x minus g of x. See, I would put an absolute value there because in here I would have f of x minus g of x, but over here I would want to take g of x minus f of x to get a positive number, see. So I would have this times h would be approximately this little increment of area. So in the limit I would expect to have a prime of x equal to f of x minus g of x. And so the area between the curves is this. Now I can do examples involving this now. Find the area between sine of x and cosine of x for x element of 0 pi. Well, what you do is you find the area up to pi fourths, then you add that to the area from pi fourths up to pi, see? And you have to split the integral because this absolute value has a different description between 0 and pi fourths and between pi fourths and pi, see? So all I have to do is compute these. Well, I know antiderivatives. This would be sine of x plus cosine of x would be an antiderivative for this integrand. That's what this is called. So then I would plug in the endpoints, subtract, and I get this is the area up to pi fourths. And the second integral I can compute the same way. And antiderivative is negative, the quantity cosine x plus sine x. So when I plug in the endpoints and subtract, I get this. So the total area is the sum of these two. And that gives me 2 times the square root of 2. And that completes this discussion of the integral. Now this is sufficient to allow you to do virtually all the problems involving integration that will come along later in the book, except you might have a difficulty in finding antiderivatives, and that will be discussed in a later chapter.